In this section on performance measurement, we shall see how to evaluate our model using its accuracy. Now we have this function evaluate, that's after training our model we have this results. Then we have this function evaluate, which takes in x and y, where y is the output we know, and then using theta gotten from our model which has been trained up to this point, we find this forward, and then with forward we simply compare if the output of the model is the same as the expected output. If it's the same, then we increase the accuracy. At the end, we return accuracy divided by m, because if we have, say, m different data points, in this case, say 10,000 data points, then we are going to count the number of times we have the correct answer, and that number of times divided by the total number of possible times will give us the accuracy, which we shall then print out. So let's run this, and there we go, we have an accuracy of 70.86. so it means out of the 10,000 possibilities, 7 out of 10 times we have the correct answer. Now let's do for the validation set. With this we have validation accuracy, which goes from 10,000 to 16,000. 10,000 to 16,000. Running this, we have the training and the validation set accuracy. From this, it's clear that we have no problem of overfitting, so our model doesn't overfit, as the training and the validation accuracies are almost the same, although the training accuracy is slightly higher than that of the validation. Let's modify our code to include the validation during training. So we define xtrain this time around. Instead of just x, we have xtrain, and we have xval, which takes all values from 1,000 to 16,000. We'll move to the learning rate intact, initial learning rate. We shall include this later on. We shall understand why this is done later on. We have the batch size, we have the output size, and then we include momentum by defining v. Here again we have momentum, so we've included momentum for it to speed calculations. You could feel free to modify for it to take ADAM or RMSProp or any other optimization algorithm of your choice. And then from here we define the validation loss at the end of each epoch. So we have the epoch loss, and we have also the epoch accuracy. And apart from this, we have, as we said, the validation loss and the validation accuracy. So we don't only calculate the loss and the accuracy, but that of the validation as well. Now for the loss is what we've been doing already. We just simply take the epoch loss at the end of each epoch, that is from here, which we have summed up through all the different batches, and then we put in this. But for the validation loss, after each epoch we take the value of theta, and using xval and not xtrain, we find the output. That's we pass this through a softmax. We calculate the loss using the categorical cross entropy loss, and then looking at the accuracy, we have the softmax again. Then we have accuracy calc. This is a function which compares the output with yval, and then tells us how accurate our model is as we go through each epoch. Once this is done, and after training over 100 epochs, these results are gotten. So this is what we have after training over 100 epochs. We see that we move from the 63 to a loss of 1.32, and then our accuracy at the end of training is 70%. Now looking at these graphs or curves, we'll see that the validation and the training set loss are almost the same as we go through the different epochs. Same with the accuracy. So it tells us clearly that our model doesn't overfit. It instead underfits, since our accuracy is quite low. Also, while doing this training, we could include the learning rate decay. that we saw on the slides. So here we'll uncomment this. We have our initial learning rate, which is defined by this learning rate. And then as we move through the different epochs, we could uncomment this now. We have the learning rate, which is the initial learning rate, times gamma to the power of I divided by the print frequency, where we could define gamma to be, say, we have gamma to be 0.8, or we could take a value like 0.9. So we have this. So our gamma is 0.9, and then as our number of epochs increase, that is, hence we're going to be having a decrease in learning rate. So we have our initial learning rate times gamma raised to the power of the epoch number divided by the print frequency. That said, we could now have the new learning rate, which is going to be printed out, and then we could rerun this model. So let's rerun this with 100 epochs. Now after 100 steps, we have this different learning rate. So we started from 1 to the power of 1 times 10 to the negative 5. We move from 9 times 10 to the negative 6, and then finally to 3.8 times 10 to the negative 6. Our accuracy has dropped, so most probably the idea of working with this decreasing learning rates wasn't the best, because it hasn't helped increase our accuracy for the same number of epochs. So that means we could take away this gamma by simply setting it to 1. So setting it to 1 will do that, since 1 to the power of any number is still 1. So we will always have the learning rate to be the initial learning rate. Or simply we could just do this. So that's it. We've just seen how to evaluate our model. For the next step, we are going to train through 1,000 more steps and see what happens. Now, we've not only gone through 1,000 steps, we've gone through 10,000 steps. After going through 10,000 steps, our loss goes from 0.827 right up to 0.8177. We see clearly that our model has converged and cannot move any further because we've moved through so many steps. Now that said, our accuracy increases from the initial 70% to 78%, but we could still consider this as an underfit. And the problem we're trying to solve is getting a character which is in black and white and then predicting whether it is one of the letters of the alphabet. These types of problems are very easily solved with different variants of neural networks, like the multi-layer neural networks and convolutional neural networks. With convolutional neural networks, we could even obtain close to 100% accuracy. So this tells us that our model isn't the best to actually understand this data set and help us do the predictions. What's also interesting to note here is, after doing the feature engineering and getting the data set with 16 different features as inputs we still don't approach even 90% accuracy with this multi-class model. Whereas with a conv layer or with convolutional neural networks, we just need to pass in the image as an input, and automatically we will get very good results, or way better results than what we have now. So let's look at our loss. We have the CCE loss, which may look like an overfit at first sight, but when we look at these values, we see that they are very close to each other. And then we have the accuracy too, which is actually very close for the training and validation sets. So to conclude, we need better models or more adapted models to understand our data set and help us do predictions which are almost 100% accurate.